this specific session, that's Introduction to RIPE NCC Educa, we have two speakers here. The first is Ferenc Csorba, who will give an introduction to routing, and after him we'll have Nathalie Trenaman, who will give an overview of RIPE NCC's involvement in routing security. So I would like to pass the word on to Ferenc Csorba, who will give you an introduction to routing. And as I said before, if you have any questions, don't hesitate to post them in the chat field.
Good morning. Before I start, can you please type whether you can actually hear me, just to see whether my microphone works? Oh, perfect. So my name is Ferenc Csorba. I work for the RIPE NCC for the Training Services Department, and I would like to give a short introduction to BGP routing for absolute beginners. That is for the next minutes, that's what we'll be talking about. And so let's get started. If you imagine the internet as being a system of interconnected networks, and imagine these networks belonging to individual organizations, although that's not necessarily the case, but let's say for simplicity's sake, interconnecting networks, each belonging to a different organization. And these interconnecting networks that belong to different organizations are called autonomous systems, and each of them gets a number. So you have these AS numbers. And so here you see all the autonomous systems, the networks of different companies, organizations interconnecting. And if we look inside one of these networks, one of these autonomous systems, then what we see is, of course, the internal network of such an organization, all kind of devices connected with having all kind of IP addresses, IPv4 or IPv6, and that's how you should imagine the whole thing. And now these AS numbers belonging to different organizations, these networks then communicate with each other using BGP. So let's have a look at BGP. BGP stands for Border Gateway Protocol. It is the routing protocol of the internet. It is the routing protocol between ASs, between these networks of different organizations. And the job of BGP is to send traffic to the correct destination between these networks. And one of the most important features of BGP is that it has AS path. So that's one of the attributes. And the job of the AS path, as you can see from this diagram, is to prevent loops. So it should prevent traffic from just going round and round and round forever. And that's the job of the AS path. So let's have a look. How does this happen? So this is one of the most simplified schemes you can come up with, what you see here. Imagine these four routers belonging to four different ASs, four different networks, organizations, and each of these routers, so now imagine what happens is router A wants to announce a range of IP addresses. In this example, it will be IPv4, but it works exactly the same way for IPv6 as well. So router A from ASN A is announcing a range of addresses, and it's announcing it to all its neighbors, and in this case also to router B in the next AS number. And apart from originating this range of addresses, this prefix, it also, together with this prefix, informs the neighbors about the AS path. And you can see the AS path there. It's very simple. It's just A. So that basically A is telling B, if you want to send traffic to these IP addresses that I'm announcing to you, then just send your traffic to A. Now this continues because B will announce, of course, it will announce its own prefixes, but we are not looking at that. We are just looking at what B does to this prefix it got from A. B will announce it to C. And what you notice is the AS path is now BA. So B is telling C, I'm announcing this prefix that's originated in A, and the AS path is BA, so you should send the traffic to B, me, and I will send it to the originator A, and that's how it gets to the destination. And this keeps going on, and here you just see it how it goes straight ahead, but of course each router announces it to all the other routers, all the other neighbors. And you can see C is now announcing it to D as well, and it says, well, if you want to send traffic to these prefixes of A, these IP addresses in AS number A, then you can send it to me, and then I'll send it to B, and B will send it to A. So that's why the AS path is CBA. But of course, C, as I said, doesn't only send it to D, it also sends it back to B. So actually it sends it back to where it heard it from. So what happens is C is now telling B, if you have traffic for A, send it to me, C, I will send it to B, and B will send it to A. And that's why you see CBA. Of course, this is absolute nonsense. So the important thing is if B gets an announcement, and in the announcement next to the prefix, it sees its own in the AS path, it sees its own AS, then it should immediately discard, trash this announcement. And that is how AS path is, loops is prevented using AS path in BGP. So, what does a router do all day long? Well, it does all kinds of things, but two of the most important jobs it does is, first, control. So control just means that the router communicating with the other routers exchanges information where it can send the traffic. So it is building up its routing tables and exchanging this routing information with other routers, in this case using BGP routing protocol to update its table so it knows where it can send traffic. And at the same time, parallel to this, it is actually forwarding traffic to the correct destination as well. So here you can see inside a router in these two colors, you can see at the top you have the control plane, and that is where the router is updating its routing tables using the routing protocol, BGP in this case, and communicating with all the neighbors and updating this information. So that is the control plane. And from that, the very simple forwarding plane is constructed in the forwarding plane, which just says if you have traffic for this IP address for this destination, then you can just send it out that interface. So that's quite straightforward. So let's have a look now how this all works. So imagine that this information that is exchanged, so these are the routes or announcements, or there are several names you can call it, and what you see in the field on the left-hand side is the actual prefix. So that's the destination where you might want to send your traffic. So that's 256 addresses there. But what you notice that next to this prefix in white, you have all the different attributes in blue. And those are the different attributes that are announced together with the prefix. I'm going to come back to this diagram, but let's have a look how this looks then if we have a look at a sort of network. So what happens is AS33, the AS number, so the network of an organization, will announce an IPv4 address range. And as I said, this works exactly the same way for IPv6. In this example, I'll just talk about IPv4, but it works the same way for IPv6. So AS33 on the right-hand side announces these IPv4 addresses, and it announces it to all its neighbors and, for example, to AS164, which is the next AS, and they will then further announce it to the third AS and then further to AS15. And you can see in router 1, now you have this route. This is what I showed you in the previous slide. And this route actually is the information, how do I get to my destination on the right-hand side in this diagram in AS33. So if I have some traffic to any of the IP addresses there. And if you look at this, let's now go back and have another look at the route. You notice that the first attribute is just called the next hop. So what is that? Let's have a look at the diagram. So the next hop is basically in the route, just says if you want to send traffic to that destination, then the next hop is router 2 in this case. So that is the IP address of router 2, where you just have to send the traffic and then it will take care of itself. And that was the next hop. But of course, there are other attributes. So let's have a look at some of the other attributes. And you can see there's the AS path attribute. And if you look at the AS path attribute, if you can find it towards the right-hand side there, you see three numbers, and you have to read it from the right, 33, 164, 756. And if you compare it with the diagram, you see those are the numbers of the three ASs, the three networks on the right, those three clouds. So basically, this means that the prefix is originated in AS33, then it went to AS164, then it's forwarded to AS756, and that is the one that told AS15, and that's where the information is now. So that is the AS path. But what we also notice, if you look at this diagram, you say, well, okay, I have now the information, so I can send the traffic along the red line to its destination. But if you look at this diagram, you see that you have not only the blue line, but you have a dotted line at the top, which can, so you could get to your destination via the dotted line and then part of the blue line, or the dotted line at the bottom. So you can see there are several routes to the same destination. How does the router know where to send the traffic? And let's have a look at the route again. You can see things like med and local pref, and you can see the med is 500, local pref is 100. So these are attributes, these are metrics, and you can see if you look again at this diagram that the different paths here have different attributes, and based on these attributes, the router will select the best path to the destination, and we'll talk about that in a moment. And so it will compare these values for the different routes, for the different announcements, and pick the best one to each destination. We'll see how that will work in a moment. So all the routers now talking to each other, they will send update messages. So they exchange these routes that you saw in the previous slides, and they will exchange prefixes with all the attributes that you saw in blue, and also prefixes or announcements that are not valid anymore will be withdrawn, and these routers will send each other keep alive messages, so constantly telling each other, I'm still alive, and the moment when the other router will not get these messages, it will realize, oh, my neighbor is dead, so I will delete all the information I got from them. And now, moving on, the most important job now for each router is to figure out from all the different routes it gets to the same destination, it will have to pick the best path to each destination. So the best path calculation is very important that each router will do. So let's have a look at this in detail. And here you see, what you see is something that's happening in the router. So you see a laundry basket. It is just a comparison, of course, and something called RIPE in. This is the so-called input routing table of the router. And I don't want to say it gets all kind of junk, but it gets all the best path from the different routers to the same destination and also to other destinations. So it gets lots and lots of routes to the same destination. That's why this routing table is so huge, and we illustrated it with this huge laundry basket. So that's the input routing table. And from all these different routes to the same destination, the router now in the next routing table, still inside the router, will have to pick the best path to each destination. And we'll see that in a moment how it will happen. So you now saw two routing tables in the router. So let's have a look at this diagram. And here you see the edge bin. So this was what we illustrated as a laundry basket where everything is put in. So you can see inside the router, it gets the updates from the peers from other routers doing BGP as well. And it has all the different routes to the same destination and all kind of other stuff. And then from this, it will pick via the best path calculation, the best path to each destination, and in the routing table, so that's the second routing table, inside the router, it will only have the best BGP routes to each destination. And then from this routing table, it will construct a very simple FIB forwarding table. And you can see it's a different color because this is now in the forwarding plane. So this is very simple. And that's how it will know where to send the traffic that it gets to the correct destination. And from the same routing table, it will tell the neighbors also which its best path to each destination are, and the whole story starts again because that's now the update to the peers. So the question is, from the edge ribbon, from this huge routing table, how do you get the best paths into the routing table on the right-hand side? And that's what I want to illustrate to you. So imagine this is of course just an illustration. It won't really look exactly like this. This is the routing table, the big routing table with all the input from the neighbors. And what you notice in the same color, each route is one line. And you notice that the first three lines have exactly the same prefix. So from these three routes, the best path has to be selected and put into the next routing table, which is just simply called routing table. And you can see from each color, you can only have one. And how is that achieved? Well, as I said, the router will look at the different attributes of these different routes and will pick the best one based on that. And you can see this is now the next routing table, the one you saw on the right-hand side. And you can see from each color route, you only have one. So each destination, to each destination, you only have the one route. So the best route that this router has picked. And from this, what happens, everything, all the attributes are then chopped off. And a very simple forwarding table is constructed. And basically, that's just really, really very simple, primitive. It says, to this destination, just send out the traffic on this interface and don't worry about it anymore. So that's the forwarding table that's constructed from the routing table. Okay, you might say, but how is the best path then picked? So let's have a look at the best path calculation. So the first input routing table gets all these routes and then it picks all the routes. So let's say picks two routes and compares them. And the way it does, it looks at the attributes of these two routes. It has to select one and it looks at this. It's almost like a shopping list and it goes down this list. Now, the first thing it says, drop if you see your own AS in the AS path. This is actually not even the part of the best path calculation. This is, as you remember, something that you do automatically. You don't even accept any routes like that. But after this, now we have the best path calculation. So you see these individual lines in the list. And what happens is the router, let's say, picks two routes from the input routing table, the adrib_in, compares them and goes through this list from the top down and keeps looking at these appropriate attributes. So it, for example, compares the weight of these two routes, and then it says, oh, the weight is the same. So then it goes to the next step and says, compares the local preference, and it says, oh, one of them has a higher local preference, so immediately there's a winner. It trashes the loser, just keeps the the winner, and it doesn't even have to go forward in this list. But if then the two routes have the same local preference, then it will have to go on and keep looking at these different criteria as long as it doesn't get to a line where the value is different and then immediately there is a winner. So that is how it works. And now what happens, it goes through all this, and perhaps the values are all the same, then it will have to start flipping a coin, because it's important to pick a winner. It's like in a kingdom, you cannot have two kings. You must have a best path to each route, to each destination. So in the end, a best path, a best route is selected, and then all the routes are compared like this, and to each destination, there is just one best path, one route, and that is the one that's put into the forwarding table. Right, so that is how the forwarding table is constructed. And from the forwarding table, as I said, it just takes all the routes and then constructs the FIB. Sorry, from the routing table, it picks all the routes and constructs the forwarding table, which is just a very simple table where it says, okay, this is the destination, I send it out on via that interface. But what happens is that if you have more specific routes, so that means if you have a prefix and another prefix that's like part of the first prefix, so they are overlapping really, and one of them is just a smaller part of the first one, then they are counted as separate destinations. So they have separate entries in the routing tables and also in the forwarding table. But what happens now? Imagine that you want to send traffic to this IP address. And this IP address is contained in both prefixes. So what do you do now as the router? Well, in the forwarding table, there's another decision to be made, and you can see it from the title. It says more specific wins. So you could say, well, I could send it out interface 2 and interface 4 because the IP address is in both ranges in my forwarding table, but actually you cannot. You always have to pick the most specific, the smallest range. So in this case, you will send out the traffic via interface 4. And this is actually how BGP routing works, a very simple beginner's introduction. What I should mention is perhaps, because I still have a few moments time, I'll just go back just to make things clear, where we saw this diagram here. So I explained how AS33 announces this range, and it then gets all the way to AS15, and there you have the route, and the route basically is just a way information how from router 1 you can get your traffic to the destination in this diagram on the right hand side. But of course this works the same way everywhere, so this keeps repeating itself. So not only AS33 will announce address space, but probably all the ASs in this diagram. And in the same way, in all the ASs, you will see routes on all the BGP routers that will have information how to get to all these destinations. So you should imagine I just explained one originator and one AS where you have the route, but you can imagine this is happening all over the place. And that is how BGP routing works. And now finally, I just want to go to the end of my presentation and just mention the fact that you saw how the forwarding table was constructed, how the best path was calculated inside each router, and finally which interface is used to forward it. And then the important thing that perhaps you should take away from all this is that BGP is decentral and self-repairing. So imagine you dig up a cable in your garden, and that's not how it would work, of course, but let's say some machinery digs up a cable, and that's where the best path was. Well, that doesn't exist anymore, and automatically you can see how this whole mechanism will immediately pick the second best now as the best in each router, and that is how the traffic will be sent to the correct destination. So BGP is decentral and self-repairing. And so this was just a brief introduction how routing, BGP routing works. And now at the end, I will just take questions. If you have any questions about this presentation, I'm now listening to your questions, and I'll answer your questions in a moment.
Thank you, Ferenc. That was very interesting. And that I think is a nice start of the day to give us a little bit reminder how it all works. Are there any questions for Ferenc? I see some people typing. Let's give it a minute, see if that's any questions. I've seen apparently today there was some event maybe at the Interxion and something went down and it repaired itself. No questions.
Well, there's one. There's one. I'll just answer very briefly to that.
So let me just read out the questions. That's such attribute as local pref, med, and other are not shared between ASs.
So I'll just, actually, it's quicker. I'll just answer talking. I'm not going to type.
Yes.
Well, we are sort of, it was like a 15, 20 minutes introduction to the basics, so I couldn't go into the depth of that. So the answer is yes, some are shared and other are not. But we don't really have time to go into, for example, local pref will not be shared, med will be shared by neighboring ASs, and some. So yeah, as I said, as Sergey gave a good answer, but as I said, I don't really have the time to go into the depth and the quick answer. Some are shared, some are not. So you'd have to look into or get some more in-depth presentation about it, because it's quite intricate what is shared and how. But as an example, local pref is not shared and med is shared, for example, between neighboring ASs if you have several connections between the same AS. And for example, the AS path is updated per hop. So as it goes from one AS to the other, the AS path gets longer and longer. The origin usually is not changed, and also like the communities are normally not changed unless explicitly changed, but that is basically the short answer. I hope that it's clear like that. So thank you very much. And if there are no other questions, then I'll say goodbye to you. I'll switch off my mic. Goodbye, everyone.
Thank you very much, Ferenc, and thank you for the questions. Then we pass over to our next speaker on the agenda. That's Nathalie Trenaman, and she is going to give an overview of RIPE NCC's activities in with regards to routing security. She's now changing seats. So I hope you can bear with us for a second. Oh, there she is. Hello, Nathalie. I hope you enjoy the next presentation, and I'll get back to you after Nathalie has started her presentation.
Yes, good morning. My name is Nathalie Trenaman. I recently became part of the product management team at RIPE NCC. Before that, I was a trainer, and I'm happy to be part of the Educa event today. I'm going to share my screen, and let's see. Here are my slides. And let's start at the beginning, shall we? There we go. Okay, so in this presentation, I give you a little bit of an update on why it is RIPE NCC is so involved in routing security and what we do to promote routing security and also make it easier for you to do routing security. Before that, a little bit of a history lesson, because a lot of people don't know exactly how things came about over the course of years, and sometimes that gives a bit of a clearer picture of why RIPE NCC and the RIPE community are so involved with routing security. We maintain, as RIPE NCC, two large tools for routing security. The first one you might know, that's the Internet Routing Registry, and that in our region is a subset of the RIPE database. So when we talk about the Internet Routing Registry, we talk about root objects, AS numbers, and prefixes. That is a subset of the RIPE database, and with that information, we recommend people, network operators like yourselves, to publish your routing policy. If people do that, then the internet community can build filters based on how it should be and what is incorrect information. Another tool that we started developing, help developing, because it's an IETF standard, is Resource Public Key Infrastructure, or RPKI, as we call it. They have the same goal. The goal is routing security. They work in a little bit of a different way, and throughout the day, that will be explained in more detail by different people. The idea is that both tools have the same goal, but they work differently. With RPKI, as the word says it, we work with a public key infrastructure, so a certification comes in place there. With Internet Routing Registry, it's more a distributed model where people create objects in the RIPE database and basically make statements with that. Not all regional internet registries all have the same tools. Yeah, oh, I have to speak louder? Oh, I have to speak louder. I thought I was already speaking loud. Okay, so they have the same goal, but they work differently. How did this all started in the past? Actually, the IRR, as we have it in our region, started the work in 1993, and it started from a RIPE document. It started with a document where people were describing why it was a good idea to create your objects in the RIPE database and make statements about your routing policy. The work started in 1993, and officially the document was transferred to a RFC draft in 1995. So if you think of it, the whole Internet Routing Registry model this year is 25 years old. So well done. It made a framework for routing security back in the days 25 years ago. Now, back in those days, everybody knew each other, and you would set up peerings based on people you've met, networks that you knew. It was mostly true if people made a statement. That is not necessarily the case nowadays. We see more routing hijacks. We will talk a lot about those later during the day as well, how they come about. But the foundation for IP routing policies in a routing registry was made already 25 years ago. Were there many enhancements after that? Not so many actually. It is still the same thing. And that's why later on, after you get more insights in routing security, in 2011, we started looking at RPKI. But let's see how many objects we have nowadays in the RIPE database. How many of those route objects do we have? And a route object is mostly a marriage, as I explain it, between a prefix and who is allowed to originate that prefix. So it's a marriage between a prefix and an AS number. And as you can see, it's not really surprising. There is still a tremendous growth of route objects, and route objects are used for IPv4. And that is partially because of deaggregation, and partially because we, as RIPE NCC, now also give out smaller prefixes. So /22s is the smallest amount and the only amount that RIPE NCC hands out, compared to a /21 that we had before 2012. So as you can see, there is a big uptake in route objects, but not so much in Route 6 objects. Route 6 objects are used for IPv6, and we recommend in all our training courses and all best practice documents to not deaggregate IPv6. So if RIPE NCC hands out a /29 in IPv6, it is recommended to create one Route 6 object for that /29. So we'd only have around 27,000 Route 6 objects in the RIPE database. Hopefully people keep in mind aggregation, and it will not go as quickly rising as the route objects. Route objects were not always easy to create in the RIPE database. Actually, we had full webinars about it. We had training courses about it. The problem was that if you had a different AS number that wanted to originate your prefix, so for example, you asked an upstream provider, can you announce my prefix? Then both parties had to authorize to create this route object. So you, as the prefix holder, had to basically provide an MD5 password for the root object, and the other party with the AS number also had to provide a password. And that was quite complicated, as you can imagine, before 2014, because people had to share passwords or find other ways around it or change passwords afterwards. In 2014, it got a little bit easier, because then we made a what we call pending state object. So the prefix holder would create it, for example, and then an email was sent to the AS holder saying, do you agree that the prefix holder is creating this object with your AS number? Sometimes people forget to reply to that email or did not acknowledge that email, and you would be in limbo. The database working group of the RIPE community decided that it was time to remove the AS authorization requirement for route and route 6 objects creation. A lot of people are surprised and say, okay, doesn't that cause a problem? But the interesting thing is by doing this, we made it a bit easier, because now it is more aligned with what we call ROAS, root origin authorization objects, that we use in RPKI, where this was already the case. So soon only the prefix holder will authorize. Made it a bit easier. Then in 2011, the IETF started working together with us, RIPE NCC, the RIPE community, to work on something called resource public key infrastructure. All the other RARs were involved as well. This is a mechanism that is used by all the different RARs. And so ERIN, APNIC, LACNIC, EFRINIC, and RIPE NCC. It's a security framework for verifying the association between resource holders and their internet resources. Basically, it does the same, has the same underlying idea as the Internet Routing Registry. But with RPKI, we attach digital certificates to these network resources, to these IP addresses. Upon request, so it's opt-in. So if you go to the LAO portal, and Tim, my colleague, will explain later on a bit more about that, you can opt in for RPKI in the LAO portal, where you can select which allocations should be certified. And once you have that certificate, you can create what we call ROAS, Route Origin Authorization Object. And basically, a ROA is a statement again between a prefix and an AS number. But this time, everything is digitally signed. So, how do we compare the creation of routes, Route 6 objects, compared to certificates. That's the first step in RPKI. You have to basically go into the LA portal and get your certificate. And the certificate number is going up. Since 2011, since we started measuring, it's going in a continued pace. You see that the other RARs are looks like they're not growing as fast, but we also have, as RIPE NCC, the highest amount of members, so also the highest number of certificates to give out. So that's also to keep something to keep in mind. The dip there that you see at the end of 2017 was a different way we started measuring things. So it was a dip, but it picked up from there again. So these ROAS, basically the thing closest to a route object. It states the address range, which AS it's announced from, but also in a ROA, what we don't have in route objects, you can specify a max length. A max length basically says what Ferenc just explained with the more specifics. There you can specify that it would be okay if you would break down your routing in smaller IPv6 prefixes. So for example, you have a /20 allocation, but you might also want to announce a separate /24 from within that /20. That you can do with ROAS, that you cannot do with root objects. Then the ROA uptake, well, it's similar as the certificates, going up and to the right, so that's good. We are actively promoting both the IRR and the RPKI, and we do have a full day training course about those topics. So if you want to know more, have a go at our training page on ripe.net to see where we have those face-to-face training courses, and we can also help you there set up those route and route 6 objects and create those ROAS. So what lies ahead in this with these two tools? First of all, we have to make it easier to create these route objects and ROAS, especially since they are becoming more feature paired, so to say. They are more aligned in what they do. And that makes that we can build a single interface in the member portal, in the LA portal, where people can create both objects on the go and have things consistent. Another thing that we promote, and that's the last bit of my presentation, the value of RPKI is actually in the last part, and not many people are doing that part already, is the validating. And Tim will explain later in the, not the next session, but the one after that, explaining what that is. Because the whole goal of RPKI is that if everybody does that, or if many people do that, you can make claims which prefixes are being sent that are valid, so stated correct, and which ones are invalid. That might be hijacks or malicious announcements. Those ones you might want to drop. And to make those statements, that is called validating. And that is not widely used yet. And that is what we hope to achieve in the coming years to improve that, so that in the end the routing does become more secure. That was my presentation for today. I'm happy to take any questions. And here's my email address. So if you have got any questions later on or any thoughts about IRR or RPKI, just drop me an email. Always happy to hear from you. Thank you very much.
Are there any questions for Nathalie? And we saw, by the way, people were asking for the files. We will upload them as soon as possible, obviously. Nathalie, I see there's one question from Rolf, which is, will there be an easier way to create a ROA for all /24s in a, say, a /19 when I want to signify that a certain route will be allowed as either a /24 or the /19, but nothing in between? That's a question for you.
Wow. So in a ROA,
Yes, I can.
Can you still hear me? Yeah. Okay. In a ROA, you can indeed specify, because a ROA is allowed to have overlapping objects. So that means that when you create a ROA, you can basically put down the prefix is a /21, and you can put a max length of /24 there, which basically means that you can announce all different /24s within that /21.
Does that
Hope that
answer your
answers the
question, Ralph? Let's wait a little bit. And while Ralph is typing, I can already tell you we're getting ready here for the next session, which is problem statement, and will be moderated by Miriam. Ralph says he has got some more questions, but he will contact you offline. Yeah, you can contact Nathalie
awesome.
by writing to
Would love to
Nathalie
hear.
at ripe.net.
Yeah.
She's very responsive.
Yeah.
Okay, then that was the end of our first session, the introduction session. I will now pass the word over to Miriam Kuhne, my colleague. She will moderate the next session, problem statement. Please bear with us, give us a few minutes to transfer speakers. We're not having a break yet. We have a break after Miriam's session, but we're just gonna change speakers and get ready for the next one. Thank you very much so far, and I'll get back to you later.